Right, everyone. In this video, we want to return to something we left off with as far as confidence intervals and a little bit of hypothesis testing. I want to talk about the relationship between the sample average and the population average a little bit more in the abstract this time. So remember, there's a story here about your population having some value that is the average height of the entire population or the average return to a particular stock in the long run, if there's a long run where you hold the stock forever, or whatever it might be that you're trying to estimate based on a sample. So I'll give you a horizontal line here corresponding to a regular horizontal axis. It's your number line. And I'll say, here's my normal distribution. Not bad, looks pretty good. The center of the normal distribution, which happens to be all three, the mean, the median, and the mode, is the letter that we usually call mu. Okay, so Greek letter M, mean, median, mode. This is the center of the distribution. It's the population parameter that I want to estimate. It happens that when I collect a sample, if the sample is large, my sample average will be very close to mu. And the central limit theorem tells us not only is the standard error going to be smaller in a large sample, but that the sample average is going to follow a normal distribution like this. That's extremely convenient because it means I don't have to worry so much about whether the data came from a normal distribution. In typical samples, this shape is going to tell me what I need to know about testing the hypothesis that the population average could be a certain number against the information that I have in my sample. So what are we going to do? Well, I'm going to grab a different color here. And I'm going to say, suppose you collect a sample. Most of the time, you're going to see a number in this range. Sometimes you'll see a number in, say, this range, way out there in the tail. Okay, that's kind of way out there. And once in a while, you'll see a number over here in this range. But we know that we can break this down based on the standard error. So I'll say, here's the population average. Okay. Here is one standard error above and one standard error below average. I'll call that mu plus SE. I'll call that mu minus SE. And based on the normal distribution, the famous number, the empirical rule numbers that we remember are 68% of the data falls into this range. So I'll go ahead and label it. That's going to be my 68%. And then if I go out a little bit further than that, say go out to 2 standard deviations, so I've got mu plus 2 SE. And on the left, the same story. Let's make that E looks like an E. There we go. On the left, the same story. Go all the way out to here. Mu minus 2 standard errors. 95.4% of the time, the true population average is going to be within 2 standard errors of the sample average, which means the sample average is going to be within 2 standard errors of the true population average. So 95.4% of the time, the sample average is going to fall into this range. This story puts bounds on how far the sample average can be from the population average. So I will make confidence intervals for my sample average based on the same story. I just simply flip this around, and instead of putting mu in the middle, I come over here and I draw it again, and I say, well, now I've got x bar in the middle, and I know that the distance from x bar to mu is governed entirely by this picture. Okay, well then, here's x bar. Mu should be in, say, this plus or minus 1 standard error range, 68% of the time, and it could be as high as 1.96 standard errors below average, or 1.96 standard errors above my sample average. In that range, 95% of the time. You'll notice that I just changed gears and said 1.96 for exactly 95% instead of the 95.4% for the 2 standard errors. We'll build confidence intervals using that reasoning. So let's try one out. Jump over here to Transformers data, more than meets the eye. And I've got 8 observations. I've got some summary statistics already built. I have the mean is here, so my sample average is 89.125. And suppose I want to come up with the average height of the entire population, which apparently includes some giant robots. No sweat, that's fine, I left them in. You'll get different numbers if you remove Optimus Prime, okay? But he's in the sample for now. The mean and the standard deviation tell me this story about the data, something about the center of the data and the distribution, the shape of the data away from the center. This data is not normally distributed. It's actually extremely skewed. We saw the histogram somewhere else, and we saw that almost all of the people are here, and then Optimus Prime is over here by himself. It's a strange distribution. But the central limit theorem says when I talk about the distance between the average of my sample and the average of the population, I don't have to worry about whether the data are skew and whether Optimus Prime is an outlier or not, because this shape, at the very least, is going to be correct for the sample average relative to the population average. Now, it's a small sample. The central limit theorem is an asymptotic idea, so we do want a large sample for the central limit theorem to really perform well, and this shape to be very precisely close to what is actually happening in the data, but it's the model that we use. So let's go ahead and grab the standard error. I'll have to make that from scratch. So in order to build some confidence intervals, like these that I've already labeled here in the spreadsheet, I'm going to make these. I'm going to make 68.3, 95, and then something like 99. So I can come up with an increasingly wide confidence interval to say, I'm pretty sure that the true number should be in this range. I'm really sure that the true number should be in this range. It gets wider as I become more confident. And then I can say I'm really sure that it's in this range. If I cast that net wide enough, I can be in the limit 100% certain that the true population average is between minus infinity and positive infinity. We never go to 100%, but the idea is there. I'm going to start with 63. In order to come up with the upper bound, I need the sample average plus 1 standard error. And in order to come up with the lower bound, I need the sample average minus 1 standard error. So I'll make a standard error. Standard error, colon. Well, this is easy. It should be equal to the standard deviation, which is this number over here, 59, which we calculated previously. Okay, I should divide that by the square root of n, SQRT. N in this case is simply 8 observations. Notice the two things that go into the standard error that are so important. How much the original data is spread out, the standard deviation, and how many observations you have. For more observations, even if the data has the same amount of noise going on, for more observations, the sample average will be closer to the truth. This is very convenient. Okay, I get 21 for my standard error. I move to the next step of the process and I say my upper bound should be simply the sample average, which is 89.125. So I'll say equals 89.125 plus 1 standard error. That would be this number. Okay, 110. Let's try the lower bound and then we'll make this the formal statement. So this lower bound should be equal to my sample average minus 1 standard error. Ta-da! And I stretch that and say there is a 68. Notice that it's also 68 here purely by chance. I'm talking about this 68. There's a 68.3% chance that the true population average is between 68 and 110. I will even draw it over here. So back to my picture here. Here's X bar. What do I have? I've got 1 standard deviation up and down. So this here is 68. This here is 110. And this is also X bar plus the standard error. And this is also X bar minus the standard error. Easy peasy. Let's make it wider. Let's stretch that out to 95% of the data. 95% of the data should be within, say, 1.96 standard errors above or below, which will look something like that. So go ahead and I remember the 1.96 number because I use it a lot. I'll go back to here. 95% confidence interval. Okay, upper bound should be equal to my sample average plus my standard error, which should be multiplied by 1.96. 130. All right. And then I'll go ahead and grab that because that looks like a very convenient formula to use again. I'll paste it here, but I want this to be minus because it's my lower bound. So now I believe there's a 95% chance, even though this sample is only 8 observations, it's a very small sample, I believe there's a 95% chance that the true population average height, even when I include Cybertronians, like Optimus Prime, I believe that the true population average height is between 47.94, so let's call it 48, and 130. Back to my picture. 48, 130. So that's x bar plus 1.96 standard errors, and this is x bar minus 1.96 standard errors. Remembering, of course, the formula for a confidence interval, 95% confidence interval for something like x bar is x bar plus or minus 1.96 SE of x bar. You'll notice that I made this confidence interval as a function of the estimator that you plug into it. So I could just as easily write 95% CI for something like beta 1 hat, the OLS regression slope, and we're going to do this. Should be beta 1 hat plus or minus 1.96, the standard error of beta 1 hat. Now we, at this point, don't have the standard error of beta 1 hat in hand, but I do have the standard error of x bar, so that's just the standard deviation divided by square root of n, and I've got it in the other story. This formula for a confidence interval is going to be universal. 95% based on a normal distribution. 1.96 is the magic number that you always remember. In a large sample, that 1.96 is going to be more or less unassailable, bulletproof. In a small sample, we will come back to 1.96 and say, I can do better. Right? I can switch from using a normal distribution to using something like a t-distribution, which looks much like a normal distribution, but in a small sample is going to have fatter tails, so it will give us wider confidence intervals than a normal distribution would, and that bakes in a little bit of extra caution. I've mentioned a couple of times that a lot of people will like to round that 1.96 number up to 2 standard deviations, or standard errors in this case. Fair enough. It's a little bit of extra caution. It seems like a good idea if you're worried. So people don't tend to complain about that. But x bar, beta 1, or any other statistic will build confidence intervals based on a formula like this. The only piece we'll really want to revisit and perhaps change is that one right there, 1.96. So back to here, I see I've got a beautiful story. I can be 68% confident that the true population average is between 68 and 110. I can be 95% confident that the true population average is between 48 and 130. Very nice. It's also convenient that the standard error is about 21, so these are about an extra 20 on each side. Nice round numbers to work with. But the next piece of this puzzle asks me for a 99% confidence interval. 68 I can remember off the top of my head because it's exactly one standard error. 95 I can remember off the top of my head because it's almost 2 standard errors, 1.96. 99% confidence. Well, I remember 99.7 was about 3 standard errors. I don't know 99 off the top of my head. So what do I do to come up with how far above or below average I need to put that upper and lower bound? I'm going to move over here to the z-score table. Now what the z-score table does is it takes a z-score which we know how to do, something like x bar minus the average, I'm sorry, x minus the average x bar divided by the standard error. It tells you how many standard errors above or below average a given point is. And I've conspicuously left those here. So these z-scores tell me that Michelle's height is 0.42 standard deviations below average. Lila's height is 0.405, maybe 406 standard deviations below average, and Optimus Prime's height is about 2.5 standard deviations above average because he's extremely tall. This tells me in a normal distribution exactly how many points should be below any threshold that you could choose. That's what I'm working with here. So I'll draw the picture again real quick. Third one, wow, so many normal distributions. Something like that. Let's do better. No better? Good enough. Something like, here's your average, okay? And I find a point, say, here. All right, this is x. And I'll go ahead and label some things. So we'll say that this is plus or minus 1 standard deviation. This is plus or minus 2 standard deviations. And I found x. X is somewhere like, and perhaps we should call it z since we're talking about z-scores. X is something like mu minus 1.2 standard deviations. Interesting. Okay, well, then when I take x and I say z is equal to x minus the average, which would be mu, let's switch to x bar just to keep that clean. X is 1.2 standard deviations above x bar. So x minus x bar, something that I can do in my sample, and I divide it by the standard deviation s. What do I get? All right, SD, there. You should be able to stare at that for a moment to think about it. You'll say, well, it's 1.2. If x is 1.2 standard deviations below average, then turning it into a z-score is just going to return the number 1.2. It washes away the units, mean and variance, or standard deviation in this case. So 1.2, all right. Regardless of what the original data units were, they are gone in the normal distribution. This point right here, 1.2 standard deviations below average, is a notable point, and this shape of a normal distribution is always the same. So let's look and see how many points are further to the left than that. 1.2? Okay, z-score should be easy to handle, right? Let's find out. So, okay, it is split up into 2 dimensions. I've got over here negative 1.2, and then if there's one more digit in your number, you can ask for 1.20, 1.21, or 1.22, or 1.23 would be this number here, but regular 1.20 is 11.5%, 0.11507 of the data falls into that range. Notice it's not a confidence interval. We're not talking about how much of the stuff is in the middle. I'm talking about how much of the stuff is over here on the left. This is 11.5% on the left. So how will I build a confidence interval for 99%? Well, I would take a picture like this. I would erase some of these annoying numbers. And I would say, I actually don't want that x or that z. We're going to need that to go away. I don't want that at all. I want to find the point over here for 99% confidence where 0.5% is on the left, and the point over here where 0.5% is on the right. I have to be careful how I draw this because I think it's going to be more than 2 standard deviations out. But in general, right, there's some amount out there, there's some amount out there. If I want to be 99% confident, then that means there needs to be a 1% chance of seeing things outside that range. We'll call that 1% alpha, which is the probability of being wrong. That's going to be type 1 error. And I'll say this is alpha over 2, and this is also alpha over 2. Standard terminology, standard nomenclature, alpha here is equal to 0.01, meaning 99% confidence. Exclamation point. Okay, well, let's find a number that'll do that. I need to find a number that leaves only 0.5% in the left tail. Can I find such a number? All right, well, it says each of these z-scores corresponds to that integral in the left tail. I want 0.5% over here, so let me find a number down here that looks like 0.005. Okay, all right, 02, 0990, 0570, 00415, 0466, okay. Look at that, 0.00508, so that's 0.0051. That's basically 0.5%. And you know what? This one is also basically 0.5%. So somewhere in between these two numbers. The second one is actually only 0.00006 away from what I want, and this number is 0.00008 away from what I want, so I suppose I'll default to this 0.494, 0.00494 over here, which is negative 2.58. Amazing. All right, let's use that information. Let's get rid of those. So this is supposed to be 2.58 standard deviations above or below average. I'll sort of patch up my picture here and I'll say that's 1, that's 2, and not the best artistic skills, but perhaps workable. We'll say that it looks very close to 3, so I'll patch up what we did over here as well. Just get that out of there and say, here's the line. This is x or mu. We'll say x bar plus 2.58 standard deviations or standard errors. And over here, 1, 2, x bar minus 2.58 standard deviations, or standard errors if we're talking about the average. All right, that will capture 95%. So I will fill that in and say, here with the rainbow pen, 99% of the data falls in that range. 99%. Confidence interval is equal to, for x bar specifically, is equal to x bar plus or minus 2.58 standard errors. Let's do it. So back to the data, my 99%, by the way, this generalizes. What we just did to come up with a 99% confidence interval would work for any number. I can do 99.9, I could do 99.99. We're asking for very strong confidence at that point, but I could do something silly like 97.5%. Okay, so upper bound will be equal to my sample average plus 2.58 times my standard error, which is 21, 143. How about that? And I'll take that exact same number, I'll drop it in here, but this one I would like to be minus. Okay, what did I do? Something funny? Yeah, A14, that's A13. Didn't need to copy paste it in that way. And I'll switch that over to minus. So I'm 95% confident that the true population average is between 48 and 130, and I'm 99% confident that the true population average is between 30, let's say 35, and 143. I can make a confidence interval of any size, and I can make a statement regarding where the population average could be. These intervals are the easiest way to build hypothesis tests, but a hypothesis test can be a bit more general than that. I'll give you an example. We'll pop back over here and I'll write a hypothesis formally. Your skeptical friend comes to you and says, I think that the population average is actually 128. Okay, well, if that's what you think, my hypothesis, which I'll write as H naught, the null hypothesis, is that mu, the true population average, is equal to 128. I don't have anyone in the sample who's 128 inches tall, but I do have people taller than that and people shorter than that, and I have some measure of variation, and I have a sample average. I can put together a standard error, and I can figure out how many standard deviations above, or standard errors, above or below average this number would be. I think I can make a statement about whether it falls into an interval I consider plausible. Right off the bat, you would look over here and say, that's not in my 68% confidence interval. So at the 68% level of confidence, I might reject that hypothesis and say, no, I think the number is in this range. I'm 68% sure. It can't be 128. At the 95% level of confidence, which is a much stronger statement, can I reject 128? Perhaps not. It does fall into that interval. Okay, so my null hypothesis is that it's equal to 28, and formally I would compare that to the alternative, which I will write as alternative hypothesis. The alternative is always the logical complement to whatever the null might be. So here, mu equals 128 in the null hypothesis, the logical complement would be not that, so I'll say not equal to 128. There we go. Simple notation for what your skeptical friend brings to you and says, I think it's 128. At the 68% level of confidence, you would reject that null hypothesis and say, no, that's outside of the range that I consider plausible. I reject your null hypothesis in favor of the alternative that it is not 128. Notice the logic here is you either reject or you fail to reject. So in the 95% level of confidence, which has a higher barrier to rejecting, because 128 is in the interval between 48 and 130, I would fail to reject. I would not accept the null hypothesis. Sometimes we joke about that and say things like Chuck Norris can accept a null hypothesis. You can accept a null hypothesis based on reasons other than frequentist inference and what I'm seeing here with the data. If you truly believe that the average height is 128 and you've got a business case that relies on that and you choose to go with that because the data doesn't tell you otherwise, you're accepting the hypothesis. But the hypothesis test is one-sided. It will reject or fail to reject. In the first case, I've got enough information. I have enough data to tell me with 68% confidence that it's not 128. But I don't have enough data to tell me with 95% confidence that it's not 128. And, of course, if I make the barrier even higher, I definitely don't have enough data to tell me with 99% confidence that it's not 128. So in each of these latter two levels of confidence, I fail to reject the null hypothesis. Doesn't mean I accept it. Right? I just can't disprove it. I don't have enough data to disprove it yet. But notice what happens to my standard error if I collect more data. My standard error relies on the variation of the original data, which is the standard deviation, and the square root of the sample size. So in every case, as I collect more data, this formula here, standard deviation divided by the square root of n, should get smaller as n gets larger. I'm assuming that the standard deviation doesn't change much. So as n gets large, the square root of n gets larger and the denominator makes this thing shrink. What will happen to my confidence intervals? They all shrink. And with more and more data, if the true population average is not 128, my confidence intervals will get narrower and narrower around whatever it is that isn't 128. So in the limit, even at 99% confidence, and then 99.5% confidence, and then even at 99.999% confidence, I would be able to reject a null hypothesis and ultimately say, it's not 128. My confidence interval is zeroing in around the truth, which might turn out to be something like 87. Okay, that's the idea for the asymptotic inference. And next, in this line of reasoning, we'll look at t-statistics, which turn the story about finding this critical value, 2.58 or 1.96, around. So we'll use the data to tell us how many standard deviations above or below. As with the z-score, we'll use the data to tell us how far away our sample average is from a hypothesized population average, and simply compare that to the z-score table without the need to make upper and lower bounds. We will be able to make a decision. So we will do that next.